Hello everyone. Today we are talking about it's an introduction to energy and work. So as always, have your formula sheets ready to go, and let's get started. So I want to start by giving the mathematical equation for what work is. Work is equal to some force applied times the cosine of theta times the displacement that is occurring for an object. So if you have a block here and it's traveling with some velocity to the right in the positive x direction, and you apply a force in that direction. So this is our force vector, and this is our displacement by velocity or what have you. It moved like, let's say, 2 meters, and then we apply a force. Work would be defined as, would be equal to the force value that's given times the cosine of 0, which, if you remember, cosine of 0 is equal to 1. So cos of 0 times the displacement. And if we think about this in terms of SI units, we know that force is a Newton. A Newton is a kilogram times meters per second squared. Meters per squared squared? No, meters per second squared. And we know that displacement is measured in meters. So we can say that work is equal to a Newton times a meter, and that is also can be written out as work is equal to joules. So the joules unit is simply newtons times meters, which can be further separated into kilograms times meters squared per second squared. So some relevant equations we have in regards to this, in regards to work, is the spring potential energy equation, where work is equal to 1/2, 1/2, times the spring constant, times the absolute value in the change of the distance of the spring stretched squared. And the absolute value brackets are important because it shows that even compression does positive work. So if you go from 0 to negative 0.15 meters compressed, you will still have a positive work done because of these absolute value brackets. One thing that's also important to note with the work equals F cos theta equation is that if you have a block here and it's being displaced some distance d, but the force being applied on it is perpendicular to the displacement, the angle here is 90 degrees, so that's a 90-degree angle, and cos of 90 equals 0. So there is 0 work being done on this block because the force being applied is not in the direction of displacement. And that would mean, according to this equation, that work equals 0 joules. All right, so let's get started on some questions. Okay, so starting off with 5.2 quiz question 1, we have 3 forces are applied to 3 identical objects undergoing identical displacement, delta r. Which force does the most work? So if you recall, we will use the relevant equation. Work is equal to the force times cos theta times the displacement. Or in this case, it would be delta r. So delta r. So let's get an idea of the angles, the cos theta, that we're going to be applying to each of these vectors, each of these vector systems. So for the first one, it seems that we have a 90-degree angle. So when we have a 90-degree angle, we have cos 90, and that equals 0. The people giving us the question were nice enough to note that cos of 60 is equal to 0.5. So cos 60 equals 0.5. And then this force is in the direction of motion, in the direction of displacement, so it has a 0-degree angle with the direction of motion. So we have cos 0, which is equal to 1. So we can then apply each of these values into the work equation, and we see that with 10 newtons of force at a 90-degree angle, 0 work is done because 10 times 0 times some displacement r is equal to 0. For the second value here, we have 8 times 0.5 times delta r, which is equal to 4 delta R. And then for this third one here, we have 6 times 1 times delta R, which is equal to 6 delta R. And by comparing these values, 0, 4R, and 6R, we see that the 6 Newton force does the most work, even though it's the least amount of force applied. It's in the same direction as the displacement, which means that the most work is done. And that is why C is the answer. Okay, so for 5.2a, I had decided to just draw out the diagram beforehand, but let's read through the question. A crane lowers a metal beam into place at constant speed. Which of the following about the work done by the gravitational force, work sub G, and the work done by the tension on the cable as the beam is lowered? So which of the following statements about work is true about the force done by the cable and the force done, or the work done by the cable and the work done by gravitational force, F sub G? So we have to consider here, as always, go back to our trusty equation. Work is equal to the force times cos theta times d. So what is true about what's going on in this situation? Well, we know that the displacement occurring is downward because the crane lowers the metal beam. So displacement is in the negative downward direction, as noted here. And we know that when the force is in line, when the force is in the same direction as the displacement, cos theta equals 1. So for F sub G, it is in the same direction as the displacement, so cos theta is cos, the angle between these two vectors is 0, so cos of 0 equals 1. But what about the tension? Well, that's in the opposite direction. That's in the exact opposite direction, so that is at a 180 degree angle, 180 degrees. And if you recall, on your unit circle, I'll just draw it out real quick. Imagine that's a perfect circle. If this is 0 degrees, where it's a positive 1, 180 degrees is on the x-axis again, but in the negative x-axis. So that is equal to negative 1. So cos of 180 equals negative 1. So when we apply these to the work equation, we see that for F sub G, work is equal to the force of sub G times cos of 0, which I'm just going to fill in as 1, times the displacement D, which would yield some positive value. Now, for the tension, we would have work is equal to force of tension times negative 1 times some displacement D. So we know that this value is negative. It's not relevant what it is given our answer choices, but it is some negative value. So if we go through our options, we know that the work of the gravitational force is positive, is greater than 0, and the work of the tension force is negative, it's less than 0. So therefore, when we're looking through these answer choices, we have to look for where gravitational work is greater than 0 and the work of tension is less than 0. So immediately I'm just glancing here. C, D, and E are all false because they're saying that the work of gravitational force is either equal to 0 or is less than 0, which is not true given the equation that we have available to us right here. So now that we're just comparing between A and B, A is saying that the work of tension is greater than 0, but that's not true because it's in the opposite direction to the displacement occurring, which yields negative work. So that's why A is false. And then B is saying gravitational work is greater than 0 and the work of tension is less than 0. And that one is true because the work done by the gravitational force is in the direction of the displacement, and the work done by the tension is antithetical, is in the opposite direction to the displacement. So that is why B is the answer. Okay, so for 5-2b, we have a spring attached to a wall. When you pull on the end of the spring with a force F, the spring stretches a distance D. How much work do you do to stretch the spring from distance d to 2d. Now, first I want to write out the spring potential energy equation. So the work done on or by a spring is equal to 1/2 times the spring constant k times the absolute value of the distance stretched or compressed squared, and that's in absolute values. And notice that for all of these answer choices, we don't have k, that spring constant, in the answer choice. So that means that some units must have been substituted out to within this equation because k is no longer there. So if we're racking our brain trying to figure out what that other equation is, we have to recall the equation for the force applied to a spring. So the force is equal to the spring constant k times the distance, the absolute value of the distance extended or compressed. And we can say that this is just distance or displacement, so that's d. So when we solve for k is equal to the force divided by the distance or the displacement. And I use those words interchangeably, but displacement is the correct term. Saying distance is just force of habit. But we can now substitute this into the work equation, and we have the equation work is equal to 1/2 times the force divided by displacement times displacement squared. And when we simplify, I'm going to come down here. Work is equal to 1/2 force times displacement, because displacement squared divided by displacement cancels out to just 1d unit. So this would be for the work done going from 0 to distance d. And that's because the delta x is distance d. So d minus 0 equals d. And that is how we got this first part. So now, when we have to consider the work done going from 0d to 2d. So the work done there is equal to 1/2 times force divided by displacement times the absolute value of 2d minus 0 squared. And we know that minus 0 is just, imagine that unit isn't there. So we have to distribute the square, and we get that work is equal to 1/2 times force times d times 4d squared. And when we distribute all this out, we get that work is equal to 2fd, because 4 times 1/2 is 2, and then displacement squared divided by displacement is just d. So now we have two values here. Work for 2d, 0 to 2d, so 0 to 2d is equal to 2fd, and then from 0 to 1d is equal to 1/2 fd. So to get from 1d to 2d, one displacement unit to 2 displacement units, we have to take the difference. So the work done from 1d to 2d is equal to the final work done, so 2fd minus the initial work done, 1/2 fd. And when we do all this math, we get that work is equal to 3/2 force times displacement. And that is our answer. And if we were to check our answer choices, D right here is the answer. Okay, so for 5.3a here, you and your friend drive identical cars. They have the same mass. You drive north 45 miles an hour. Your friend drives south at 45 miles an hour. Which statement is true about momentum and kinetic energy? So recall that momentum is equal to the mass of the object times the velocity, and kinetic energy is equal to 1/2 times the mass times the velocity squared. And this is important. This is the squared value here, because when we're considering velocity, negative velocity when squared becomes positive. So a negative times a negative, so -1 times -1 equals +1, positive. However, for momentum, the velocity unit is not squared, so direction would impact the momentum, yielding a positive or a negative value. And if we consider this situation, we have some initial starting point, and we have you going in a positive direction north at 45 miles per hour. And you have your friend, which I will color in red, going 45 miles an hour in the opposite direction. So we could say negative 45 miles per hour, because this is a velocity unit, so direction matters. So when you plug each of these into the momentum and the kinetic energy equation, your momentum, so I'm going to bring it back to blue, your momentum is equal to P equals 45m, and your kinetic energy is equal to 1/2 45 squared times m, whereas your friend, which I will go back to red for, and I'm going to do this in the corner here, the momentum is equal to negative 45m, but the kinetic energy, when squared, the negative times the negative, you get a positive value, is still 1/2 45 squared m. So therefore, the momentum is the same, or the momentum is different, they're in opposite directions, but your kinetic energy is the same, as we can see here. This is their kinetic energy, and this is, where is it? This is your kinetic energy. So your kinetic energy is the same as their kinetic energy, because when velocity is squared, the negative unit is canceled. However, since momentum does not have that squared value for velocity, the negative impacts the momentum, meaning that the answer choice that would be relevant here is the one that says that the momentum is different, but kinetic energy is the same. And we see here, answer A says have the same momentum and kinetic energy. That's false, because that does not consider the direction at which the objects are moving. You have different momentum and different kinetic energy. That's false, because we have the same kinetic energy as we had shown in these equations. We have the same momentum but different kinetic energies. This is the most false answer. And then D, your car and your friend's car have different momentum and the same kinetic energy. That one is true. So that is why D is the answer. This next one here is asking us to evaluate a velocity versus time graph and convert it to a kinetic energy versus time graph. And we have to recall, I'm always going to write them out. Kinetic energy is equal to 1/2 mass times velocity squared. And as we had just discussed, when we're considering the velocity and converting it into a kinetic energy value, any negative value, so as you can see here, this is in the negative direction, is canceled out when converting to energy, because a negative times a negative equals a positive value. So any of these graphs that have kinetic energy decreasing in the negative direction are automatically false, because we know that when a velocity value is squared, when a negative velocity value is squared, we will yield a positive kinetic energy. So A and D are already false. I'm going to go to red to cross out these a little easier. And we know that the velocity value is squared, so when we're relating kinetic energy to velocity, kinetic energy is directly proportional to velocity squared. However, kinetic energy, the square root of kinetic energy, is proportional to velocity. So therefore, we don't have a linear relationship going on, and that is why E is false, because we have the relationship between kinetic energy and velocity is not linear. It is quadratic. And therefore, when we're looking for the answer that most aligns with this information, we see that C is the answer, because as velocity increases, let's say velocity increased by a factor of 2, so we had 2v squared, kinetic energy would increase by a value of 4. So kinetic energy would be multiplied by a value of 4. So we could say that this was like 1/1, and this is, if we double that velocity, we could say that the kinetic energy increased by more than a factor of 2, because if we kind of like bring this to the axis, I would say, I don't know about you, but I would say that this difference here, so the difference from point 1 to point 2 on the kinetic energy axis, on the y-axis, this is more than, I'm going to do this in another color, let's do brown, this small difference here. When we're comparing these, I would say that these two differences are greater than a factor of 2, whereas the difference from 0 to 1 and from 1 to 2 is about equivalent. So that is why C is our answer. Okay, so the next question we have here is 5-3C. A ball with mass m and a ball with mass 2m are both dropped from the same height above the ground. Both experience free fall. Which statement is true about the two balls as they hit the ground? Answer A says the ball with mass 2m has a larger speed and a larger kinetic energy. B says mass with 2m has a larger speed, but the balls have the same kinetic energy. C says the balls have the same speed, but the ball with mass 2m has the larger kinetic energy. And D says the balls have the same speed and the same kinetic energy. Well, first let's address the more relevant part of this question as it relates to this lecture, and it's the kinetic energy portion. And we can just plug in the values of m and 2m directly into the kinetic energy equation to determine which one would have a higher amount of kinetic energy. So for ball with mass m, we can say, so for situation 1, we can say that kinetic energy is equal to 1/2 1m times velocity squared. So this simplifies to 1/2 mv squared. And the second ball, has a kinetic energy equal to 1/2 times 2m times velocity squared. And this simplifies to mv squared. And we can say that mv squared is greater than 1/2 mv squared. So ball 2 with mass 2m should have a greater kinetic energy than the ball with mass 1m. Now let's consider the speed at which they hit the ground. So recall that when the only force acting on an object is the weight force, the force of Earth's gravity on an object, it experiences free fall. So when an object is in free fall, the only force is its weight force. And that weight force is equal to mass times gravitational acceleration. And this gravitational acceleration portion is important because no matter the mass of the object, the acceleration on the object is the same, negative 9.8 meters per second squared. So objects with different masses will accelerate at the same rate, negative 9.8 meters per second squared, negative 9.8. So their velocity versus time graphs should be identical. So I'm going to do this in a different color. So this is the x-axis here, and then that bottom line is the terminal velocity, let's say. And they both start at 0, and that slope over time is negative 9.8. So this is a velocity versus time graph. And regardless of the mass, it'll experience the same increase in velocity over time, or it becomes more negative over time until it hits the ground. Since they're both dropped from the same height, they should experience the same velocity, the same speed, as they're about to hit the ground. So this would be 2m, this would be m. They both experience the same velocity as they both have been falling for the same amount of time because they both have the same acceleration due to gravitational acceleration, meaning that they both have the same speed. And summarizing this information, we see that ball 2 with the mass 2m has a greater kinetic energy than ball 1, but ball 2 and ball 1 have the same speed. So when we're looking at our answer choices, we see that C is our answer because it says these balls have the same speed, but the ball with mass 2m has larger kinetic energy. And as we showed through our diagrams here, that is the case. The last question we have here is 5-3 quiz question 1. A ball is rolling at 4 meters per second and has a kinetic energy of 4,000 joules. If the ball's speed doubles to 8 meters per second, what is the kinetic energy? Now there are two ways of solving this. You can simply solve for mass and then plug the mass into the new equation. But I don't like that way. I feel like that way does not help us understand the mechanism or the relationship between variables. So, as we had stated previously, kinetic energy is directly proportional to velocity squared. So if you were to double velocity, you increase kinetic energy by a factor of 4. because if we can say kinetic energy is proportional to 2v squared. When we distribute that squared, kinetic energy is proportional to 4v squared. So velocity increased by a factor of 2, but kinetic energy, it would have increased by a factor of 4. So when considering this, I'm going to erase all this to clear up some space. At a velocity of 4 meters per second, so 4, we had a kinetic energy of 4,000. But when we double that, when we double it and it goes to 8, we should see that kinetic energy should increase by a factor of 4. So this increased by a factor of 2x, and then the corresponding kinetic energy should increase by a factor of 4x, 4 times. So that means 4,000 times 4 is 16,000, which is why C is the answer. And we can verify this by plugging in these values into the kinetic energy equation, and I'll do this live on my calculator. So 4,000, I'm going to do it right in this corner. 4,000 equals 1/2 m4 squared. That's a 4. Multiply 4,000 by 2 to get rid of the 1/2. Divide by 4 squared. 4 squared is 16. So we have a mass of 500. Mass of 500. And since this is in joules, it's 500 kilograms. Yikes. We can plug back in 500 into the 1/2 mv squared for this next one. So kinetic energy is equal to 1/2 500 times 8 squared. So 500 times 1/2 times 8 squared, so 8 squared is 64. We get that is equal to, so kinetic energy is equal to 16,000 joules. And as you can see, we verified this in 2 separate ways and showed that 16,000 is the answer, and that is why C is the answer. The last question we have here is just asking us to consider different types of energy, different types of work taking place, and how they're transferring from one form to another. So recall that energy is neither created nor destroyed, it is converted between forms. So heat, you can apply heat to a beaker of water, and the particles speed up, meaning that their kinetic energy increases. So we turned heat energy into kinetic energy within the water. You can have a change from potential energy to kinetic energy if you throw something off a building, like a ball. And there's a bunch of different types of work. You can convert spring energy into kinetic energy by having a compressed spring push a ball, and then that ball now has a velocity. So understanding the interplay between different types of energy and how they're converted from one to another is important. So let's consider the transfers of energy, what forms of energy are being converted. So a ball gains speed as it falls from the top of a building. So a ball is up here, it falls. So it has some height h. So we can consider the potential energy equation. So the potential energy is equal to mass times gravitational acceleration times height. And that is converted, that potential energy is converted into kinetic energy because that ball is gaining a velocity. It started off with no velocity, and now it's gaining a velocity. So that potential energy, as height decreases, so as height decreases, velocity increases. So potential energy is being converted into kinetic energy. So now, our second one. A box is connected to a rope. A box connected to a rope is lifted off the ground. So we can see that the direction of motion is upward, and the force is upward as well. So the work done is positive. So the work done is positive, just to recall some of the stuff we've mentioned earlier in this lecture. And on top of that, we are increasing the height. So I'm going to do this in a different color. Height is increasing. So we are adding potential energy to this block here, to some mass m. So an outside force is increasing the amount of potential energy on this specific block. If we did not consider that that lifting as a part of the system, we could say that an outside force is increasing the potential energy of the system. And the third one, I'm going to draw out a diagram in another different color. So this is our guy here, and let's say it went down a little. And we have this guy initially down here, and he walks up a flight of stairs. So he's going up and to the right, up and to the right, up and to the right. So the direction of motion is at a 45-degree angle. We could say this is our direction of motion, and the force being applied is to go against the force of gravity. So gravity is downward, and our force of this guy's legs, his beefy legs, is upward, and it's greater than the force of gravity because he's able to walk up the stairs. So we can say that this angle here is theta, and there is work being done to get up a flight of stairs because this angle is not equal to 90. So because this angle is not equal to 90, there is some amount of work being done, and since, I'm going to go back to our red color, since we're increasing in height, this person is gaining potential energy because they are getting higher, and they are doing work in order to gain potential energy, and that is why the energy of getting up the stairs is being converted into potential energy. And that is the last question we have. So just to summarize, the first one, the ball falling, we have potential energy being converted into kinetic energy. The second one, the work done to lift the box is converted into potential energy. And then the third one, work done to lift the mass of the person against the force of gravity is converted into potential energy. So you are exerting a force to overcome the force of gravity, and by doing so, you are increasing your potential energy because you now are higher. And yeah, that is our question set for the day. Thank you so much for watching. Hopefully you enjoyed. If you did, please leave a like, and have a great day.